Are you able to neglect X?
No.
No, because what?
Because the K value is large.
Yes, the K value is large. You cannot neglect X. And how do you solve?
It's the algebra.
Algebra. You love algebra. Okay, so what we previously said was that, and I'll show you how to shorten up some of your words, not that much shorter, but instead of writing ice down, you can actually write ice like this, and just do 1 molar, because they were all given as 1.00 moles per liter. Right, 0. So then Q is just CO2H2 over CO and water, and this is water vapor, or steam, so water vapor. So when you plug ones into all those, the Q is equal to 1, which is less than K. So that's why we said proceed right, because in order to create a situation where Q is equal to K, meaning it's at equilibrium, you must increase Q enough to be what K's value is. So that means you need more products in the numerator. So that's going to be proceeding to the right. So then you just subtract X, add X, add X. So I just wrote it all in one line versus in a chart, which is the same thing. So when you plug everything in, you get 5.1 is equal to 1 plus X squared over 1 minus X squared as a simplification, right? Because you just plug these values in for products and these values in for reactants. We here so far? You good with me? Okay, so then you square root the whole thing, and that's 2.258 is equal to 1 plus X over 1 minus X. You could, at this point, plug this into your solver. Once you show me that much, I'm like, okay, I'm pretty sure you can solve for X. It's going to take a little manipulating, but you could plug it into your solver. But how do you guys have to plug in your solver? How would you have to do that?
You have to do 1 plus X in parentheses divided by 1 minus X.
In parentheses.
And then minus 5.
Right, so minus the number. And so that would set it equal, or yeah, minus 2.258. And that would set it equal to 0. Some other people's solvers might be different. I can actually just plug that whole thing in like that and just say solve for X, and it will. So if you want to solve for X, that's totally fine. If not, you got to bring your denominator over, distribute, combine like terms, and I can show all that, but I'm hoping that we're good with this. X is what? What did you guys get so far?
0.386.
I got 0.386, yeah. No one in there. Okay, so then we got X. Molarity, right? Because X does have a unit. So the question though is, what is the equilibrium concentration of all the species? So what would you need to do with X now?
So plug it back in.
Right, so you'd plug this value in for X here, 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 and here. And generally, to make your life a little easier, you can just write carbon monoxide's concentration equals water's concentration, which equals 1 minus X. So that's 1 minus, that is 0.634, 0.614? 14, right? Okay. And then separately, carbon dioxide, which equals hydrogen gas, is equal to 1 plus that. So that's 1.386 molar. Cool. Not hard. Easily done on your test for free response. The next one, let's see how this one's different before I proceed. Tell me your first couple steps, and then we'll kind of move on from there to another type of question. Maybe. Number 11, what would you need to kind of, exercise 11, what would you kind of need to start first? Okay, so you got your BCE, you could do. What else?
Find the concentrations.
So how do you find the concentrations?
20.0 moles divided by 1.5 liters.
Right, so moles divided by liters, that was your original or initial molarities. You also have the K value being 1.15 times 10 to the second, which is fairly large, meaning what?
It's probably going to go towards it.
Well, first of all, you know products are favored. You should have more products. And then what should you do with your initial concentrations given?
Plug them in the Q.
Plug them in the Q, and you would find that actually, so 3 divided by 1.5 is
2.
2, and this is formation of so it's formation of gaseous hydrogen fluoride from hydrogen and fluorine. So diatomic hydrogen fluorine equilibrates to hydrogen fluoride. So it's 2 of those. So then whenever you set this up to be 2 molar, is it given for all of them?
Yeah.
Yeah.
For each component.
So 2 molar, 2 molar, and 2 molar. Q,
Q equals 2.
yeah, Q does equal, no,
Or
Q
no.
equals 1,
Wait.
right? Because, and I know that you guys are math savvy, but I do recommend you setting up your expression every single time so that you don't forget the squared nature of some of the reactants or products. So here, this is going to be 2 squared over 2 squared, so that is going to be 1 when you plug it in. So then 1 is less or greater than K. Way less, right? This is like 115. So that's less than K. So which way does it proceed?
Towards the product.
Towards the product. So then you're subtracting X from the reactants and then adding, yes, making sure you're adding 2X there because it's a true coefficient. And then from there we can plug into the K expression and solve for X. I just want to make sure we're good with figuring out how to proceed. So we're proceeding right there. All right, 12 is actually what I wanted to get to. So start on number 12 for me because it deals with partial pressures, and a lot of those I think are, when you change up units, sometimes it's a little scary because you're not sure if you do the pressures. So go ahead and take 5 minutes on that one. If I do it with you, it might be a little helpful. Tell me what you guys have written so far. H2 plus I2 yields HI because it's hydrogen iodide is synthesized from hydrogen gas and iodine vapor. So 2 of those. Okay. Clayton, what else? What were you saying?
Then you just put the concentrate, the partial pressures into the iPod.
Okay. So partial pressure is given for everything. And then Maggie, what you were saying, I'm going to get in a second. So this is hydrogen gas. This is 1 times 10 to the -2 atmospheres. The iodine is 5, and I know there's more sig figs. I just don't have any room, so forgive me. 5 times 10 to the -3 atmospheres, and hydrogen iodide is 5 times 10 to the -1 atmospheres. Okay, so we got our initial setup. What else do I want to set up first?
The equation just equilibrium constant.
So the expression, and do I have anything else given to me? Thank you. Sorry, the equilibrium constant. So yes, you do have the liters, but you're given the equilibrium constant as well, right? And that one doesn't say it's KC or KP. So I assumed it was KP because all my pressures are given, all my units are given to me as pressure. So because it doesn't say otherwise. So KP is, what is the expression for KP?
Or partial.
No, the expression is like the actual products over the
Partial
reactants.
pressure of
Yeah.
HI.
Of HI.
Over.
Whoa,
Squared.
Over.
Partial pressure of hydrogen. Partial pressure.
So every single time you want to find KP or KP is given, it does not mean you have to use that politically correct formula. KP is to the KC, RT to the delta N. It's like you have to convert between the two. This one is the expression for it. So those are the initial concentrations. What else do I need to do now? And this value, sorry, is given. It says where the equilibrium constant is 1.0 times 10 to the second. So that's what KP is equal to. So I need to do what now?
Find Q.
Find Q. So if we plug those values in, this and the top square divided by those two, you get Q to be, so I would just assume that you guys can plug those values in. Q is 5.00 times 10 to the third.
So that's greater than our K, so we proceed toward it.
So that's greater than K because K is just this little guy here. So if this is greater than K, you must proceed to the, yeah. And so react, I don't know, I want to write proceed left. Proceed left towards the reactants. And that's going to cause us to subtract from which side? So what are you subtracting here? 2x, and then adding x and adding x here. Okay, so then we take those values. Can we neglect x? Probably not, because the k values, you know, it's 100, so it's high. So you're still going to have more. You can see relatively, you still have more products than anything else really. So it's agreeing with the k value. So you're probably not going to neglect. And then so when you start to plug into your k expression, I'm just going to write this as 100 is equal to partial pressure. So 0.5 atmospheres. I don't really need to write atmospheres. Sorry. So this is 0.5 minus 2x squared over 0.01 plus x, 0.005 plus x. I'm just showing you different representations. It's the same thing. What do you want to do to solve for x? Mathematically. Can we simplify this expression at all? Huh? We'd have to FOIL the bottom.
Teachers, pardon the interruption. Bus 117 just arrived on the campus. Please allow those students to your classroom.
So we'd have to FOIL the top and the bottom. You notice we can't just do a simple square root of everything. We're probably going to have to do the quadratic equation, right? You will have to do the quadratic on this one, but you can also plug this into your solver if you're not a quadratic person. So you can take what you have here, parentheses galore, subtract the 100, set it equal to 0. So when you do that, you get x is equal to 0.0355. Okay, and that's, what's the unit on that? Atmospheres, right? So that's the atmospheres, and the question specifically asks for. That's not work, guys. It doesn't want to work right now. The equilibrium pressure of all species, so that should indicate that you should still be in the unit of pressure, so that's helpful. So then you just plug in your x value where it belongs and solve for each of those equilibriums. Okay? There's one more thing I was going to ask here for you. Oh, if I wanted you to find the concentration of the species, what would we need to do? And solve for Kc, right? And then use that expression, and then use these things. These pressures, though, would not be in the icebox. What would we have to do with each of those pressures? Class to find the concentration of everything.
Use PV equals nRT to find the moles of each gas, and then divided by
The liters given, right. So if I ask for concentrations, you'd have to take this pressure, plug in the PVs and RT, and solve for moles over liters to get you concentration, and then that's what you would put into the Kc expression and so forth. Okay, look at for D, A and D, A and B, that you just did for homework last night. The question seemed, I think it scared some of you guys, but it was not something you had to do a lot of math for. It was basically looking at the K value and the Q value and deciding if it proceeded left or right. So, oops, where is this thing at? And this will be the last thing I go over before we start lab. I'll go over the other one if I need to later. So, whenever you guys can see this fairly well, when you had this reaction, you had solid, solid, and gases, the question gave you Kp as 1.04. Oopsies. 1.04. So whenever you look at that, your initial information given, it was given 2 concentrations or moles of the solids, which don't matter. Solids are irrelevant to equilibrium. The pressure was given as 2.25. Well, since K expression is partial pressure of CO2, and the initial concentration or partial pressure of CO2 was given as 2.25, that is Q. So Q compared to K, Q is greater than K, so what has to happen? Right, it has to proceed to the reactant side. So as you proceed to the left, you must consume products to make reactants. So as you consume products, the amount of CaO or calcium oxide should decrease because you're consuming it. Some of us were working real hard on that one, and I appreciate your effort, but this one actually is not too bad. Questions on A? Yay, nay? Nay. Thank you. One person said nay. Same thing for part B. This one gave us the K, or the partial pressure of carbon dioxide as 1.04. So that is what Kp is equal to. So Q is equal to K. So what does that tell you?
Yeah, equilibrium.
It's at equilibrium already. So if it's at equilibrium, then there is no shift. So then the amount of CaO does not change. Cool? Wow, you're like, I tried way too hard. And it's okay to try hard because you learn from your mistakes and then you have more tools in your tool belt. Okay, so next thing is lab. So pull out your lab. Tell me what the tell me your 3 main steps to this lab. We should have read it and have a general idea. First step, first main step. So you're preparing a series of standard solutions. Oh, so actually, hold that thought. Lab notebooks, everybody has your lab notebook. Yes. You guys have to do me a favor and go back and add procedures to things, and I'll give you back points for adding procedures. Because methodology on how to complete these labs is important, and it was from day one we were putting like brief descriptions of the technique, and now I'm printing the procedures so they're nice and small, and you can tape them in your lab notebook, and you don't even have to write anything down for the procedure. I think Zonky is probably the only person that has like almost every procedure. Thank you. Because you just cut it out and take the procedure in there. So please remember your lab procedure or your lab layout, and this is for college. It's not from me, it's because the College Board recommends it. You have your title, easy. Your purpose, 1 blurb, 1 sentence blurb. You can even need the purpose I type out, just print it out, or take it in there. Safety, a quick blurb. Procedure can be a quick blurb, or it can be like a pretty detailed one, which is, of course, just taping it in your lab notebook. So there must be at least a technique noted in there. So for this first technique, what is it? You said prepare a series of dilutions, and what are we doing with those? You're measuring the absorbance. So we're measuring the absorbance through colorimetry, okay, of a series of iron thiocyanate solutions. Next step. So why are we doing that, by the way? You guys should be looking at your lab, not me. Why are we doing that? Huh? So but we know the concentrations, and we're measuring the absorbances. So what are we doing that for?
To make a Beer's law.
To make a Beer's calibration curve. This is probably the 50th time we've done this, right? So this is, of course, a very important concept. You should be creating a Beer's calibration curve. Second step, what are you doing? Second step, second part of the procedure. Okay, so you're determining the concentration of unknown sample based off the absorbance, and then you're comparing that to your plot of your calibration curve. Okay, so part 2 depends on part 1 being very accurate. Okay, part 3. Preparing solutions to do what? To do what? Okay, so find the absorbance, but what are we going to do with that? Okay, so basically our substance that is colorful is iron 3,5-cyanate FeSCN. The colorless species are the 2 preceding that. So iron 3 it's clear to pale yellow, depends on which year it was that I made it. Yours will be fairly colorless. The iron or the potassium thiocyanate is colorless. When they come together, they make this deep dark red color. But of course, this is an equilibrium reaction. So in that third part, you're making you're forcing the reaction to occur. It's making this iron 3 thiocyanate, and it's red. You're measuring the absorbance of that, right? But from the absorbance, what can you determine? You were telling me. You determine the concentration, and that's the concentration at equilibrium. So what are you measuring? You're actually calculating the concentration of that at equilibrium. So technically, you could go back and find the concentrations of those at equilibrium as well, based off an ice chart. Okay, how many trials or how many different reactions are you doing in part 3? 5? Because I think the first one has 0 though. So kind of 4.5. So how many ice boxes are you gonna make? 5 different ones. Okay, and that's because everything's gonna have a different concentration. So I recommend you get all your data, and you guys are gonna have to be in groups. You're gonna have to be in 5 groups today because I only have 5 colorimeters. Okay, and you make sure you get all your data. I'll show you where everything's in the back, and then data crunching. You'll see this weekend I just have lab analysis, and for anybody who wants to start early, I'm handing out your holiday packet in case you have time. Okay, so it's up here, and I'll just take them for you on your desk. All right, so let's go. You guys form 5 groups in less than a minute. Go. Form 5 groups.
Okay.
And somebody can have it up. No, actually not. We have 17 people, 5 groups. 4 people in a group. 4 people in 2 groups.
So, okay, so right now, in 4 groups of 3, 1 group of 4, and these come back later. 4 groups of 3, and 1 group of 4. Okay, go. We'll be group 4. Sorry.
Okay, got it.
Alright, you can keep it off. Come grab a calculator and come grab a handful of volumetric. And I will have logs to computers. Grab 4 volumetric flasks. 4 volumetric. Guys, if you need any beakers or anything, look underneath. Honors how to use quite a bit of things behind you. If you need anything from the back, I will. What I would also do for your group is designate 1 pipette for iron substance and 1 pipette for the calcium thiocyanate substance. And clean them out in between. There's 1 group missing a color here. 1 group. Not going to get a color here. You guys need it. I gotta get a shot. Hey, and I did this thing at Charlotte, art teacher, right? You just have what down you need for each part. They do. How much you need of those? I'm gonna do that. I don't know where it's right now, but I think it's.
Hey, guys, you can use volumetrics. Use your volumetrics. Just get a little bit of each of the solutions for now and beakers, and then go from there.